Hello champions, welcome to Diksha Karnataka YouTube channel. So today I am going to discuss the first chapter of first PU, which is units and measurement, and here we are going to discuss in detail, in depth of all the concepts. So maybe you are someone who is studying in first PUC and want to revise this chapter, or someone who already moved on to second PUC, but for your KCET preparation, if you want to revise this chapter, you are also welcome. So both for PU1 and PU2, this is one of the most fundamental foundational chapter. You should not skip this chapter, because based on this chapter all the other chapters are developed, right? So if you don't know unit, you will not be able to understand anything that is coming for in future chapters, right? So the units and dimensions both are super important for your class examination, as well as the price target of KCET examination and JEE, NEET, whatever exam that you prepare along with it, right? So this is the foundation of each and every chapter. So that's why you have to pay little bit more attention to this chapter. And as I mentioned you that I will try to cover this chapter in a detailed way. So please buckle your seat belt and let's start with the journey. So first let us look into the roadmap of the chapter, what all the concepts that we are going to discuss in our session for the day. So basically we have divided the chapter into 4 distinct parts. Part 1, units and SI system. This is the basic slightly historical concept. Next we will be going into the significant figures. Then we will be discussing basically arithmetic and uncertainty principles. Okay, so this is these two are super duper important, and dimensional analysis. So what are all the dimensions and dimension analysis? So if you are only here for revision, or you are studying in second PUC and you want to revise it, then you should focus mainly on part 2 and part 3. These are super duper important. If you are studying in PU1, by the way, you have to go through all 4 parts. There is no exception to that, right? So let's start with our journey. First, units and international system. Okay, so journey of units. So just to give you a context, when in the ancient times we used to measure things using our hands, bodies, feet, etc., right? So one length, one arms, one finger length. Okay, so this is we used to call it like this. We used to measure also in our childhood, also we used to measure 1, 2, 3 like this, right? So then later on we had started using some standard measurement systems. Okay, because these are not standards. So suppose there was some cruel person who wants to grab everything and they don't want to give you back the enough value for it. They used to cheat people by saying, okay, this much he will bring someone having a very large hand and say this is only 5 hand, whereas someone will say no, this is 10 hands. So like that. So there are a lot of inconsistency in that. So people started doing things in a more measured way, and they started measuring the ground, field, etc., in more systematic way, so that no one can cheat and everything is balanced. And in pursuant of that, there are many systems which came into place. Okay, we are going to discuss that as well. Okay, so measurement is comparison with reference standard. Okay, so as I mentioned, initially there was no standard. We used to use our hands, but that is not a standard. If you consider a standard person's hand size, it varies from person to person. You can check your hand's length with another friend's hand. You will see that someone's hand is bigger than you, someone's hand is smaller than you. But if you standardize it, saying that okay, there will be one single standard, this much length, we will call it say 1 meter, then that is fixed. So there has to be some standard. Okay, the standard is basic, arbitrarily chosen. Arbitrarily chosen means suppose I say this much length is 1 meter. Okay, this length, suppose I am saying this is 1 meter, even though it is not, for sake of explanation, let us assume this is 1 meter. But this 1 meter, why it is called 1 meter and why this much is not called 1 meter? that is arbitrarily chosen. Someone somewhere said this is 1 meter, and that standard persisted, and since then that length is now considered 1 meter only. Okay, so this was arbitrarily chosen. There was no scientific reason that why 1 meter, why not 10 meter as 1 meter, or say 1 centimeter as 1 meter. There is no such reason whenever it was assumed, because mostly that length was mostly in use, and that's why this was called this much length is 1 meter, and we still today use that as 1 meter. Arbitrarily means no scientific reason is there, okay, but internationally accepted. So whatever arbitrarily chosen, that is now internationally accepted, then that is called standard basic thing called unit. Okay, so unit is which is it was arbitrarily chosen, and the reason may be historical, reason may be some practical, reason may be some experimental as well, but whatever the reason it was chosen arbitrarily. There was no proper scientific explanation behind that, but now that is universally accepted, internationally accepted. So everywhere you go 1 meter, if I say 1 meter in India, the same 1 meter will be still there in UK or in USA. No matter wherever you go, 1 meter will be standard, that is sure. Every measurement result has 2 steps. So when you are measuring something, it can be length, it can be mass, it can be time. So whatever you are measuring, it has 2 quantity. Okay, first is a number, okay, numerical measure, and it will accompany with a unit. Okay, for example, here we have a length. Okay, length is 5 meter. Okay, so 5 is the number part and the meter is the unit part. So if we say just 5, it has no meaning. It can be 5 meter, it can be 5 minute, it can be 5 second, it can be 5 kg. So 5 as a number is just a number. So in mathematics, we say 5, 6, 7, 8 numbers. But when it comes to physics, we have to add a unit to it. Okay, we have to add a unit to it to make it valid. Okay, so we will say 5 meter, 5 kg, 5 second. They are 3 different quantities at all altogether, right? So if you are not adding proper unit, that does not make any sense. So you have to add unit, because you are not in mathematics class, you are in physics class, right? So physical quantities are interrelated. So so that is also one important part. What is a physical quantity? Physical quantity means whatever quantities that we can measure. Okay, it can be mass, it can be length, it can be weight, it can be anything. Whatever we can measure, we can call it a physical quantity. Now, can you give me one example that which cannot be measured? For example, my dream. Okay, I dream big, or say I dreamed a lot yesterday. So can you measure the dream? No, right? Can you measure the thought? I am thinking very beautiful things in my mind. Okay, can you measure that thought? No. So those are not physical quantities. So physical quantities are those which can be measured. Okay. Now physical quantities basically are interrelated. Not all the units, all the physical quantities are independent from each other. So if you know one unit, one quantity and other quantity, you can find, you can mix them and find a new quantity. Okay, so physical quantities are interrelated. We will see that throughout our journey, all through all the chapters. So physical quantities are interrelated. I will give you one example, which is very basic, is speed. Okay, speed is distance by time. Okay, distance traveled by time. So distance traveled in unit time is called speed. So if you want to measure speed, you just need to know the distance and how much time it has taken to cover that distance, right? We have done that in our lower classes. So that means speed is a dependent quantity. Okay, so it is many other quantities can come together to give you a new quantity. So physical quantities are interrelated. So we do not require separate units for all these quantities. Okay, so if we define certain standard quantities which are fixed, okay, these are called basic units, and any other units which can be derived from those units are called derived units. Okay, we will see one by one. So let us start with fundamental or base units. Okay, units of the base quantities. So units of the base quantities. So the quantities which we say that they are fundamental, we require them. Any other quantities can be measured using these quantities. They are called fundamental quantities. So if you know only these quantities, units of these quantities, any other quantities can be measured. Any other quantities can be measured. That's why they are called fundamental units. Okay. So they are independent, they do not depend on anything else, okay, not defined via other units. Okay, only 7 in SI. We will come to that. What are all the units? 7 in SI. So 7 units in SI system are basically fundamental units. So here the units are given: meter, kilogram, second, ampere, Kelvin, mole, and candela. We will see what are all these quantities. Don't worry. What is the derived units? Derived units are all other physical quantities which can be derived using fundamental units. Okay, whatever units we can derive using fundamental or base units, they are called basically derived units. Okay, expressed as combinations of base units. For example, speed is given by meter per second, force is given by kg meter per second square. So even though in force we call it Newton, Newton is not a fundamental unit. Newton is a derived unit. If you break it apart, you will see that 1 Newton equals to 1 kg meter per second square. Now it is very large name to pronounce. That's why for certain quantities, okay, we give them certain special names based on certain name of some persons. Okay, mostly Newton, Joule, Watt, etc. Okay, so there are many of such quantities. One fundamental quantity is based on also not one, two fundamental quantities are also based on the name of two persons. Okay, if you know which are those, mention in the comment below. Right? Let us move on. So system of units, the complete set of base units plus derived units gives rise to set of units. Example: CGS, FPS, MKS, SI. Okay. So what is CGS, FPS, MKS? Let us look into this. CGS refers to centimeter, grams, second. That was a unit which was most prevalent in our country, CGS system. Okay, it is also called Gaussian system. Okay, when British came into India, they actually brought CGS as well as FPS system, but CGS system somehow become popular, even though FPS system was in use in India as well. Okay, even some cases we still use FPS system. Anyway, so CGS and FPS both were popular in India. CGS means centimeter, G for grams, S for second. Okay, length is centimeter, mass is gram, time is second. Okay, so this is a so initially, just to give you context why other quantities are not mentioned over here. Initially, it was thought that only 3 fundamental units are there: length, mass, and time. Later on, the other 4 were added. They realized that okay, we require more than 3 fundamental units, and then the other 4 were added into this list. Okay, that's why CGS, FPS, MKS, all these 3 systems, they have only length, mass, and time unit. Okay. Now FPS system is most popular in UK and British era. When British was ruling the most of the world, they brought this unit system along with them in the all parts of the world. So FPS is foot, pound, and second. Okay, so foot basically come from the length of a standard distance of foot or of human feet. Okay, from there this unit foot came. So foot, pound, and second. Still in many places you will see this use of foot, gauge, okay, pound, second, etc. Second is obviously common, but foot and pound are also some cases we use. Half pound cake. Okay, if you visit a bakery, you will say half pound cake or 1 pound cake. So this pound unit is still in use. It is a measurement of weight. Okay. Now MKS, it is a precursor of our modern SI system. Okay, here length is measured in meter, mass is measured in kilograms, and time is measured in second. Now one important point, be it CGS, FPS or MKS, in all system of units, you will see that the unit of time is same. Unit of time is same no matter what system you use. This is second, this is second, this is also second, right? So time was always same. Time, there was no doubt that we will measure time in minutes or in hour. No, time, basic time is always second. Okay. So all three were extensive use until recently. So as I mentioned, CGS was popular in India after independence. Okay, FPS was brought in to India by Britishers. Okay, and MKS was also in use many parts of the world, including India also. CGS and MKS was popular because you can convert CGS to MKS easily. Now why MKS is important? Because MKS, in case of MKS, meter, kilogram, second, they are slightly bigger units compared to CGS. Length is small, gram is small. So that's why if you want to say everything, express everything into CGS, basically you have to convert the data back to MKS. So CGS, even though it was popular, CGS and MKS combined together are actually considered to be one single unit, because they can be considered converted from one unit to another. So 1 meter is equal to 100 centimeter, 1 kg is equal to 1000 grams. So those conversions were possible. So that's why these two were popular. But FPS, as I mentioned, FPS is completely different system, which was made popular by Britishers, and all three systems were in use, and still in some parts, in some cases of measurement, still they are in use. But when you are talking about international exchanges, suppose you want to buy something from America, or if you want to sell something to America, then these units will not work. You have to have a standard unit that is prevalent across the globe, and that unit system is called System Internationale des Units, Systeme Internationale des Units. Okay, so this is basically our SI system. So if someone asks you why we call it SI system, international system, so it should be IS, right? International System of Units. It should be called IS. But the convention or the meeting where all countries came together, okay, and they decided what will be the standard unit system. It happened in France, and the resolution whichever was passed was written Systeme Internationale des Units. Okay, and that's why it is called SI system. Okay, it is historic reason. Okay, the name still persists. Okay, it is, nobody changed it to IS. Okay, it is only SI only. Okay, French for International System of Units. Okay, French for International System of Units, but because it is in the manual, when it was written, it was mentioned Systeme Internationale des Units, so it was adopted as SI units. Okay, now developed by BIPM, International Bureau of Weights and Measure, in 1971. So till 1971, all sorts of different units were in use. So if you want to do international business also, back then it creates a lot of problem, because different countries have different measuring systems. So in 1971 onwards, slowly the world started adopting this system, revised by General Conference on Weights and Measures in November 2018. So if you are someone who is following the international newses, there was a very huge news in 2018 where they have changed certain references. The values did not change, the unit system did not change, but they have changed certain references, okay, with respect to which they were measuring. So for example, there was 1 kg. If you want to measure 1 kg, so there is a standard 1 kg bar which is placed in a museum, okay, in I think Greenwich Museum or some museum, I am not sure. So there is a 1 meter 1 kg bar made of platinum and iridium, kept in a 0°C room temperature, and that used to be the standard of measurement. Okay, if anyone wants to create a 1 kg measuring device, he has to go there, take the exact value, take the measurement, compare it with this, and then create replicas. Okay, those replicas were sent to different countries. Okay, in India also, India had a replica, and from that replica, all the other measuring weights. So if you still until recently, if you visit a shop, okay, they will measure using, okay, 1 kg. This is your grapes. Take it, right? So they used to use physical balance. Now everything is digital balance. Okay, most of the places. But if you go to some old markets, you might still find the physical balance present there. Okay, so physical balance, the weights. Okay, the how do they get that weights? That weight was actually based on some internationally kept at certain room temperature in a international museum, and that museum actually created replicas of those weights and sent it to different countries. Okay, uh, and same for length also. There was a platinum iridium rod, and between those two rod there are two markings. So those two markings are is considered as a 1 meter. Okay, and but that was complicated. So every time you want to you have to check whether it is actually standard or not, if the value have changed or not. So that is very critical and difficult. Okay, these are all historical aspects, but very interesting. So that's why they change the standards with respect to which they are now measuring the length, etc. So that standard change happened in 2018, which was a very big news. Okay, now used in scientific, technical, industrial, and commercial work worldwide. Okay, so if you want to do business in anywhere in the world, you have to follow this international system of units. Now this is decimal based. Why this is popular? What is the major reason of this being popular? Even though FPS would have been adopted, because FPS was British people ruled almost half the world, so many people, many countries actually using FPS system, but still we chose SI system over FPS system. Why? Because it is decimal based. Okay, conversion within the system are simple and convenient. So meter to centimeter, centimeter to meter, meter to kilometer, kg to grams, grams to quintal, tons, etc. They are easy to do, and that is the major reason. We do not want to waste too much of our brain, too much of our time only by when we are converting units. So that is why we wanted a simpler unit system, which we do not need to remember any factor. Okay, so for example, if you want to go and buy a flat or a plot, they will say square feet. Okay, this is a 1000 square feet plot. Okay, so what is the meaning of 1000 square feet? How much in meters, etc.? That requires a lot of calculations, and your brains will freeze. You will say 1000 square feet, that means a lot. Okay, but if I say square meter, 100 square meter, that means 10 meters by 10 meters. You'll have an idea about it, right? So, so to remove those complications, international exchanges, international trade happens based on international unit only. Okay, now 7 base units, 2 supplementary units, we will come to that as well, and infinite derived units. So derived unit has no limit, it is infinite. Okay, practically there are thousands perhaps, but theoretically there could be infinite derived units as well. Now what are those 7 base units? So I am talking about this for a long time. So here is time to reveal the 7 base units. First is length. Its SI unit is meter and symbol is small m. Okay, so length is the distance between 2 points. Obviously we know that. So that is meter and unit symbol is m. So if I say 10 m, that means 10 meters. Okay, mass is obviously how much matter is present inside a body, which is given by mass. Its unit is kg, kilograms, and its symbol is kg. Okay, time is obviously we measure time between two different events, right? So time is measured in seconds and symbol is s. Okay, there are bigger units, obviously. Only one unit where you require certain level of conversion is second. Okay, 60 second is 1 minute, 60 minute is 1 hour, 24 hour is 1 day, like that, right? But still, other than that, all other units are easily convertible. Next is ampere, which is electric current. Okay, electric current means how much current is flowing in a circuit, how much current is flowing in a wire. Okay, that is measured using ampere. Ampere is the name of a scientist. As I mentioned, there are two units in SI system which is based on the name of person. Ampere is the name of a person, and its symbol is capital A. Now, when write ampere, if you are writing the entire AMPERE, make sure this A is in small letter. If you write this A in capital letter, that will suggest the name of the person, okay, who actually did a lot of research in current electricity. So that will refer to that person. So do not use capital A. A should be small letter. Okay. Next is temperature. Temperature unit is Kelvin, and its symbol is capital K. Again, Kelvin is named after Lord Kelvin. He also did a lot of research. He developed his own temperature scale, which is Kelvin scale, and that is internationally adopted as well, and its symbol is capital K. Okay, capital K is the unit of temperature. Next is amount of substance. Amount of substance is even though mass refers to amount of matter in an object, amount of substance is also considered to be a fundamental unit because it is independent of mass. Okay, so if you know that 1 mole of every object have same amount of particles. Okay, for 1 mole carbon have mass, say 1 gram mole of carbon have 12 gram mass. Okay, 1 gram mole of oxygen have 16 gram mass approximately. There are some plus minus obviously, but say, okay, so gram moles of 12 gram mole of carbon is equals to 16 gram moles of oxygen. Okay, so that means in terms of substance, number of substance present in the object, that also has to be a fundamental unit. So that's why it was later on added in the amount of substance as a fundamental unit, and its unit is mole. Okay, 1 mole, 2 mole, 3 mole, you all do it in chemistry. So the application of this is mostly in chemistry, not so much in physics. Okay, and another is luminous intensity, the brightness, how bright a light is. Okay, so that is measured using luminous intensity. So the light, there is a definition of it as well. So from certain distance, how much brightness it is, how bright it is, how much power it is emitting. So that is actually luminous intensity. Now sometimes, for example, in the previous generation lights, okay, when we are using incandescent bulbs, okay, that bulb with having a wire, okay, even though they are consuming high amount of energy, they are not so bright because their luminous intensity was less. Okay, when it was brought down to the newer generation of LED lamps, okay, with even smaller power, the lumen or the luminous intensity is much brighter in those lamps. Okay, so luminous intensity is not dependent on the power of the source, how much power it is consumed by the source, it depends on something else. That's why it is considered a fundamental quantity. The use of this is very less in our modern day, except if you are studying some say optical engineering. Okay, if you become an optical engineer, maybe in that case you need to study more about this luminous intensity. Otherwise, the usage of this unit is very less, but yes, it is an important unit to understand a new quantity, right? That's why this is also considered a physical quantity, fundamental quantity. Okay, now let's move on. Base definitions. Okay, the base definitions, there are 3 important definition is meter. Okay, so how we define meter now? Previously it was distance between 2 lines drawn on a platinum iridium rod. So all those units are now replaced with physical, instead of physical measurement, it is replaced with some constants. Okay, some well known constants. For example, meter is now defined using the speed of light. Okay, speed of light is a fixed quantity, and the value of speed of light is taken to be 299,792,458 meter per second. This is a very exact value. Okay, so if you allow light to travel for 1 second, it will travel this much distance, and if you divide that distance by this number, you get 1 meter. Slightly complicated definition, but this is for the betterment of physics and measurement. Okay, we will not dependent on physical. Suppose that museum where everything is stored suddenly fall under earthquake and destroy everything, then how we will come back and how we will measure the length. So this is a standard way of replacing old measuring devices using international standards. So this is a definition. Now kilogram is basically based on Planck's constant. Okay, Planck's constant and mass can be related, and from there 1 kg is defined. Obviously the definition is not important, but you should remember that meter is linked with speed of light, kilogram is linked with Planck's constant, because obviously if you are from PU1, there might be some MCQ questions where they will ask you that kilogram is based on which of the following standard constants. Okay, so you have to identify Planck's constant is related to mass. Seconds is basically represented with the frequency of vibration of a cesium 133 crystal. Okay, so fixed cesium 133 hyperfine transition frequency. Okay, so this is slightly complicated thing, what is transition frequency, etc., but you should remember cesium is can vibrate very fast, and that's why cesium clock, the clock that you wear modern, the analog clocks are actually based on vibration of cesium, and that clock is very precise, and this is super fine. So the frequency is measured, and based on that the second is defined. Okay, so in 1 second these many vibration of cesium occurs. So this is a very huge number of vibrations. Okay, so if that many vibration occurs, then it is called 1 second. Okay, that is interesting. Ampere is fixed value of the elementary charge. Elementary charge is charge of an electron, 1.6 into 10 to the power of minus 19 coulomb. So based on that, ampere is defined. Kelvin is fixed value of Boltzmann constant. So Kelvin comes from the Boltzmann constant, which is also a constant. Mole is exactly Avogadro number of elementary particles. So Avogadro number is 6.022 into 10 to the power of 23 per mole. Okay, this many particles per mole. So this is based on Avogadro number. Next, candela. Candela is fixed luminous efficacy at 540 into 10 to the power of 12 hertz. Okay, 1 candela is equal to 683. No, not 1 candela, sorry. This is the constant, which is 683 lumen per watt. Okay, this is also some standard, but it is not super important, as I mentioned. First 3 base units, how it is linked with different constants are important, because based on that you might face a MCQ question in future. Now let's move on with 2 more units. Now plane angle and solid angle. Now plane angle and solid angle, they are actually, later on you will see that their dimensions are 0. They do not have any dimensions. Okay, they actually do not represent anything which is physical thing, but yes, we still use these units. Especially suppose you have a line over here, another line over here, you are measuring how much is this angle. Okay, so that is also considered as supplementary units. Later on, as I mentioned, it will be considered to be dimensional quantities, but still it is considered as a supplementary unit. Okay, so if you see in future where it is mentioned that dimensionless but has a unit. Okay, the quantity is angle. Angle is a dimensionless quantity, but it has a unit. So this is theta, represented by theta, and its unit is radians. Okay, radians is SI unit. In our normal life we use degrees, right? Degrees is also can be considered as an angle of units of angle, but we always use radians. Most SI cases we will use radians. Now another important thing is, if this length is ds, okay, the radius of the, if this length is ds, this is called arc length, radius of this is r, then this angle d theta, okay, can be calculated. D theta equals to ds by r, and ds equal to r d theta. This is a formula that can be used from time to time in many derivations, but just remember it. Okay, if you are preparing for JEE exam, this can be very handy. Next is solid angle. Solid angle is basically plane angle comes into picture when there is a line, okay, curved line, and we have a point. So what is the curved line making an angle at the center? Okay, so this is a two-dimensional thing. Now instead of having a two dimension, if I have a surface, area of ds or dA here, okay, what is this surface area makes an angle at the center? Okay, what this surface area makes at the center? So that is given by solid angle, which is a two-dimensional angle. Okay, this is a solid angle, which is a two-dimensional angle. Here it is angle is two-dimensional, solid angle is three-dimensional. So the solid angle is given by dA upon r square. Solid angle is given by dA upon r square. It's like a cone. The shape is like a cone. Okay, shape is like a cone. If you take a cone, ice cream cone also, the bottom part of the ice cream cone, that is a solid angle. Okay, so the top part is very huge, but the cone is very small. So solid angle is small. Okay, so in that solid angle, whatever is the length, based on that you can fit a lot of things inside. Solid angle is also used in many cases, not up to your graduation. When you move into the graduation, there solid angle will come into picture. Till then solid angle has no uses. Okay, solid angle has no uses until you move into graduation. So maybe it is in your engineering, maybe if you study physics or mathematics, there you will use solid angle. Till then no use. So just remember, solid angles unit is stay radian. Solid angles unit is stay radian. Okay. Now units retained for general use outside SI units. So some of the units that we use in our day-to-day life. Okay, our day-to-day life we do not always use SI units. Okay, so some of the units, for example, minutes, 10 minute, 5 minute, 10. Then we have year. Okay, year is also not a standard SI unit. Okay, ton, TONNE ton. Okay, TONNE ton is 1000 kg. Okay, 1000 kg, that is 10 to the power 3 kg. There is another unit which is called ton, 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 that is 100. He has scored a ton. Okay, in cricket it is used, ton, 1 ton, TON, ton means 1000. 100. Ton means 100. TONNE ton means 1000. Be careful. Okay, TONNE ton means 1000, TON ton means 100. Okay, there was one KCET question where this unit was used, 1 ton, TONNE. So TONNE means 1000. So there is one extra n. That means the value is also high. If the only single ton, TON ton, the Yuvraj Singh, those who remember Yuvraj Singh, used to play with the bat which is written a ton over it. Okay, so that is I think maybe 100 kg bat. That's why it was mentioned ton. I don't know. Okay, so some players play with the bat where ton is written over it. Maybe a sponsor, maybe a bat manufacturer. Who knows? I don't know. Anyway, Curie is used in terms in the activity. Okay, so, we will that is not part of the syllabus anymore, but maybe you will learn in chemistry what is the Curie unit for, what is radioactivity, what is activity, etc. Okay, hour, another unit. Okay, 3600 seconds. Day, 86,400 seconds. That is also a unit. Degrees is not a standard, but you use it in almost every measurement, especially in our day-to-day life, right? Another is liter, 1 liter, 10 liter, 5 liter, right? So in case of water, liquid, petrol, etc., we use unit liter. Liter is 10 to the power of -3 meter cube. Carat is 1 carat gold, 1 carat diamond. Especially it is for carat is CARAT. Carat is used for the measuring of diamond. Okay, 1 carat diamond is 200 milligrams. Sorry. Okay, we use bar to measure pressure. Okay, pressure unit, it is 10 to the power of 5 pascals. Okay, we will see that in future when the time is appropriate. Pascals is the unit of pressure. Bar is also used, 1 bar, 1 millibar, 2 millibar, etc. Okay, barn is a unit of area, small unit. It is used for barn. Okay, now in the past there was areas where used to keep animals, they used to call barn, and the standard size of one animal keeping areas is based on barn. So that's why it is somewhere it is used. Another one is hectare. Okay, 1 hectare, 2 hectare, so many hectares of crops were wasted this year because of the drought, right? So hectare is unit of area. Again, its unit is 10 to the power of 4 meters square. It is a huge area. Okay, 1 hectare, 2 hectare. Okay, another was acre also is used. Okay, 1 acre, 2 acre. So hectare, acre, they are units of area. So there are some common units. Not, you don't need to remember everything. Just for your understanding that even though SI units are there in our day-to-day life, we sometimes use units which are not limited to SI units alone. Okay, now let's move on to our second session, second part, which is basically significant figures. Okay, now we will discuss significant figures. So we will see why do we need significant figure, what are the uses of significant figures, what is this, everything we will discuss in detail. So let's start. Okay, every measurement, what is the meaning of measurement? Measurement means you have a device. You have a device. Using that device, you are trying to figure out how big, how long, how small, how heavy some object is. Okay, so that is called measurement. Measurement can be done in different things. So how much is the distance between Bangalore and Delhi? Okay, so that is a measurement. You have to use a tape and measure it. Okay, there are other ways to do it. Obviously, we do not measure length between two cities using tapes, but yes. Okay, so if I say the how big is this pen is, okay, so you have to use a tape and you have to measure it. That is called measurement. So in every cases, whenever I say that as my pen is bigger than your pen, so how you will say that? If I say my pen is bigger than your pen, you say no sir, my pen is bigger, I have a longer pen. Okay, so some people will bring a very long pen and say my pen is bigger. So how do we say someone's pen is bigger or longer or anything like that? So that means you have to do some measurement. Exact measurement gives you a value of, okay, this is longer, this is smaller, this is shorter, like that. Okay, so every measurement involves errors. So whenever you measure something, there will always be some error. Okay, some is intended, some is not intended. There may be some instrument error based on because the instrument is faulty. Okay, if you visit a shopkeeper, he is giving you say 1 kg mangoes, but you came back home and you measure it, you see only 900 grams of mango is there. Okay, so that means the shopkeeper's measuring device is faulty and he will say, oh, this is an error. Okay, you have to leave me because this is an error, I cannot help it, right? So every measurement contains certain error. Okay, report results, so they indicate the precision of the measurement. Okay, so up to certain value the device can measure perfectly, and beyond that the device cannot measure this correctly. Okay, reported number, all reliably known digits plus first uncertain digit. Okay, these together equals to significant digits, significant figures. So for example, I will give you one example here. From now on, everything is going to be scientific. Okay, no more history, no more random discussion. Suppose you are measuring a length. I am giving you the example of length only. So you are measuring a length. Okay, while you are measuring the length, okay, suppose this is the object. Now you are using a scale. You are using a scale. Okay, this is your scale, you measured it. Okay, so your scale is this. Now when you measure it using the scale, you see, okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, so if you measure this length, now let me redraw it. When you measure the length of the object, you started from 0. and your measurement ends over here. Okay, so you will see that the length is not exactly falling between the numbers. So say this is my 1 2 3 4, 1 2 3 4 5 6 7 8 9 10 11 12 13. So if you see the result here, okay, the result is this measurement is not exactly falling either on it is more than 12 for sure, but it is less than 13. Okay, I should probably draw a little bigger line. Okay, I should probably draw a little bigger line so that it is clearly understandable. Okay, just give me a moment. So, okay, suppose this is 1 2 3 4 5. Now the length that you are trying to measure is this. Okay, now when you are trying to measure this length, you will see that this length is is more than 4 but less than 5. Okay, in between also, in between these lengths you have some smaller data, say 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8, 4.9, 4.10. Suppose this is like that. Okay, so here you see that this is between 4.2 and 4.3. So you will say that the result is 4.2. This is for sure, this is certain. This much is known. So this measurement is 4.2. This is obviously sure, and then it is between 2 and 3, but it is close to 3. So I am saying this is 4.28. This result is not certain. This is uncertain digit. This digit is uncertain. Why this is uncertain? Because we are guessing it. Okay, we are not able to tell exactly whether it will be 8 or 7 or 6 or 5. Okay, and even if we are able to tell it, there will be certain level of uncertainty. So this is uncertain digit. This is called uncertain digit. So 4.2 is definitely known. Okay, this is certain digit. Okay, this is certain digit. This is certain. Certain means confirmed. Okay, this is uncertain. For example, when you are writing physics exam, you will say that, okay, in physics, I will score 70, so definitely up to 75. So 70 is your certainty. Okay, 5 is your uncertain digit. So 75, if I say 75, 70 is certainty. 5, if I get one question correctly, I will score 75. If I don't get that question correctly, maybe 71, 72 like that. So that 70 is fixed certain number, and the extra 5 is uncertain number. So same with measurement as well. So there is a level of certainty, and beyond that there is a level of uncertainty as well. Okay, certainty and uncertainty together gives you a significant digit. So these 3 digits together, all these 3 digits together is called significant figure. We call it sig fig. Sig fig. Sig fig is significant figures. Significant figures basically comes from the measurement. If I just say a number, say 2.25, okay, it has no significant figure because it is not a measurement. Only when we say this is a measurement, say we are measuring a mass and this is coming out to be 2.25 kilograms, then it is a significant figure. Okay, only as a number there is no significant figure. Significant figure comes precisely from the measurement of quantity. Okay, so reported number has all reliably known digits. So 4.2 is reliably known digits. The first uncertain digit is called together is called significant figures. Okay, precision depends on the least count of the measuring instrument, obviously. So in our case, the precision was dependent on least count. We can measure 0.1, 0.2, 0.3, but not 0.1, 0.1. Okay, so extra digits beyond these are superfluous and misleading. Okay, if I say 4.282, so that is not meaningful. 4.282 has no meaning because that 2 is completely absurd. So anything beyond that measurement is basically superfluous. So here is one example. Pendulum period. Okay, 1 and 6 are reliable and certain, and this digit is actually uncertain, and together there are only 3 significant figures. So significant figures, as I mentioned, comes directly from measurement only. Okay, length of an object, say 287.5 centimeter. So 287 are certain, already known, and 0.5 is uncertain. Together they form 4 significant figures. So if they give you that 287.5, what is the uncertain digit? The uncertain digit is 0.5 actually. Okay, so these are all very tricky but simple concept. Okay, now when you change the unit, suppose you measured it in centimeter, you want to convert it into meters, okay, or you have measured it into meter and convert it into centimeter. Okay, no matter what unit you add, the significant figure rule does not change. So changing units does not change the significant figures. Okay, so changing units does not change the significant figure. The significant figure should remain same no matter what unit system you are using. So here is a measurement 2.308. So this is a measurement which is in centimeters. If you convert it into meters also, the significant digit should remain same. If you convert it into millimeter also, significant digit should remain same, and in micrometer also the significant digit should remain same. Okay, so no matter whatever unit you will use, the significant digits should always remain same. Okay, significant number should also remain same. Okay, golden rule: a choice of change of different units does not change the number of significant digits in a measurement. The location of the decimal point is of no consequence. So here where the decimal point is located does not matter as long as it's a measurement. Okay, and if you know that the original measurement has 4 significant figures, no matter whatever unit you will use, the final result still will have 4 significant figures. Okay, now let's move on with counting rules part number 1. So now we have to count significant digits. So there are few rules to understand significant digits, and in the exam there will be they will ask you write 2 rules or 3 rules of understanding or of determining significant figures. So you have to memorize them, understand them, because based on that questions might also be asked. They will give you a number and they will say how many significant figures are there in that number. So that type of question is also very common in Q1. Okay, so what are the rules? All non-zero digits are significant. No matter what, if the digits are not zero, they are all significant. You cannot say call a number, say 1, 2 or 3 or 5 or 7 or 8 or 9. They all are significant digits if they are not zero. So for example, 1, 2, 3, 4, all digits are significant. So the 4 significant figures are there. So if the number is given, a measurement number from a certain measurement is given to you, and they will ask you how many significant figures are there. So you have to say, okay, here we have 4 digits, 4 significant figures. So you have to count 1, 2, 3, 4, right? 4 digits, 4 significant figures. So each digit consists of 1 figure. Total number of digits, total number of figures. Okay, so figure means how many significant digits are present in that number. In a number, how many significant digits are present, that is called significant figure. Okay, 4 significant figure means 4 digits present. Okay, now zeros sandwiched between 2 non-zero digits are also significant. So for example, here 2.308, okay, or 2.308 or say 1005, every number are significant. All the numbers are significant. Okay, so here how many significant figure? 1, 2, 3, 4. here 1, 2, 3, 4. So you cannot exclude zeros if the 0 is coming between two digits. For example, say 5, 5, 0, 0, 1. Okay, so how many significant figures? 1, 2, 3, 4, 5. So 5 significant figures are there in this number. So all zeros sandwiched between, sandwiched means, so if you see here, this 0 is coming between 3 and 8. So this is a sandwich, right? Sandwich, 0 and 8, right? Here 1 and 5, between 1 and 5 there are two zeros. So no matter how many zeros are present, if their starting number and ending number are non-zero, then all those zeros you have to count. So they are all significant. Even though they are zeros, you have to count them. They are all significant numbers. Leading zeros for number less than 1. If the number is less than 1, any leading zeros are insignificant. For example, if you write 0.002308, these zeros are insignificant. They are not considered as significant figures. Okay, so if the number is less than 1, if the number is greater than 1, by the way, if same number is written, say 1.002038, so in this case, this is coming out to be sandwiched number. This is a sandwiched zero. So these zeros are significant. These zeros are significant, including this also. All the zeros are significant here because they are sandwiched. But here, if you remove this one, so 002308, these zeros are not significant. These zeros are not significant. Only 1, 2, 3, 4 significant digits are there. Okay, now this 0 is significant because this is coming between 3 and 8. So be very careful when you are doing significant figures, when you are dealing with zeros. 0 is the most complicated thing in significant figure. Okay, so 0 can change whether it will be I am significant, I feel I am significant, or he will say I feel I am not significant. So even 0, say if you score a number 100 marks, those zeros are significant. But if you score only 0 marks, they are not significant, right? So when you are writing an exam, if you score 100 marks, all zeros are significant, right? But if you score say 10 marks, zeros are not significant. If you say I score what was your score in physics? 0, 0, 0, 0. Is it significant? It is not significant, right? But if I say no, I scored 100, significant. Just giving you an example, not physics wise, just for life wise, real life wise. Okay, same goes for physics as well. Some zeros are significant, some zeros are not significant. So if the number is less than 1, then and the leading zeros are not significant. So this 0, including this, is also not significant. Okay, none of them are actually significant, but this is significant. This is sitting between two numbers, so he is saying I am safe. Okay, this 0 is saying I am safe, I am between 0, 3 and 8. You guys are sitting alone, so you are not significant. Trailing zeros without a decimal point are not significant. Trailing zeros means zeros which are coming late. Okay, so even though I said 100, all the zeros are significant, but that is mark wise. When you come to physics, 100 only have one significant figure. Very interesting. So if I say 123 meter, let's convert it into centimeter. It becomes 12300 centimeter. If you convert it into millimeter, it will say 123,000 millimeter. But as I explained previously, changing units does not change significant figures. So even if you change the units, the significant figure does not change. So that means the each of them have only 3 significant figures. Okay, each of them have only 3 significant figures. So zeros which are coming last, they are not significant. Okay, they will become significant with a specific rule, but without that specific rule, all the zeros which are coming last are not significant. And if the number is less than 0, any 0 before the number in the trailing zeros, they are also not significant. Okay, trailing zeros with a decimal point are significant. So these two are the most important point and most confusing thing. Okay, so if I say 12300, they are not significant, but as soon as I put a decimal over here, they all become significant. Okay, they all become significant. If I add a 0 over here also, all these zeros are significant. Okay, so these 3 zeros are all become significant. So if you want to make 0 significant, what you have to do? You have to put a decimal, right? If you want to make your 100 significant, you have to put a decimal at the end, then those zeros are significant. Okay, so 3.500 and 0.6900, so these zeros are significant. These zeros are significant, even though they are not. Okay, they are we call it leading zeros. Leading zeros are not significant, but trailing zeros can be significant if it is sitting on a decimal number, even if they itself it is 0. So for this example, 1, 2, 3, 0, 0, 0.0, even though last 3 digits are 0, all of them are significant. Remember this. This is very, very important. All of them are significant if there is a decimal involved. Decimal can change your fate. So you need a decimal. If you are scoring 0 in physics, you need a decimal in your life. Okay, and if you put that decimal, then your zeros will become significant, right? Let's move on. The trailing zero trap. Okay, so trailing zero is little difficult, so that's why we are putting a little bit more effort into it. The trailing zero trap, reported length for 4.700 meter. The zeros convey the precision of measurement. Precision of measurement means the result is very accurate, 4.7 only. Your device could measure the result up to 4.7, 1, 2, 3, like that. But you are getting a very accurate 4.7. So if I say 4.700, that means your result is very accurate, very precise, and the device that you are measuring can measure up to 3 decimal points, but right now it is only measuring up to 1 decimal, because the remaining data is actually exactly matching. So this represents the precision of measurement, and that is why these 2 zeros are put over here. Your device can measure up to 3 decimals, but your result is exactly 4.7, which is amazing, right? So if they weren't, we would simply write 4.7 meters. Okay, so 4.700 meter has 4 significant figures, which is very, very important. Now even if you change the unit from meter to centimeter, or centimeter to millimeter, or millimeter meter to kilometer, you will see that we will maintain these 2 zeros at the end no matter what, and all these zeros become significant. Okay, now here one important point, when you convert meter to millimeter, it is becoming 4700. Now we know that the trailing zeros are not significant without a decimal. So these 2 zeros should not be significant, right? So 4700 millimeter has trailing zeros with no decimal. Okay, rule says only 2 significant figures, but a mere change of unit cannot change its decimal point. So this will still have a 4 significant figures. So to understand that, what we have to do, when you are converting meter to millimeter, to maintain the significance of the all digits, you have to put a blank decimal. You have to put a blank decimal. Okay, so this is sometimes we write a number with a blank decimal without anything after that. So for example, if I say 100 point, this is a decimal, but after that we are not writing anything. That means these zeros are significant. This represents these zeros are significant. Okay, so also in future we will learn about scientific notation. They are also important, just coming in next part. Okay, so when we want to make sure to represent these zeros as significant, we add a decimal at the end. This decimal is not put there by mistake. This decimal represents that these zeros are significant. So when you convert one unit to another, okay, there can be some cases where you find that the significant digit changes. So 4.700 meter, when you convert into millimeter, it becomes 4700 millimeter. 4700 millimeter means last two zeros should not be significant. But original data has 4 significant figure, the final data should also have 4 significant figure. That's why we have to put a decimal at the end to make sure this is also significant, the zeros are also significant. So the blank dot we use to denote, especially in case of zeros, we use the blank dot to show that the zeros are significant. Okay, interesting. Scientific notation. Scientific notation, we write every measurement as a into 10 to the power b. Okay, so this is very common notation that we use in our life. For example, charge of an electron is given by 1.6 into 10 to the power of minus 19. Okay, this is a scientific notation. Instead of writing 0.00000, obviously how many zeros we do not know, and then last 1.16 does not make any sense. So this is much simpler and easier to write. Even though this is a very small number, this is very significant, very important number. Okay, and this has a significant figure. How many significant figures are there? Answer that. Okay, so here whenever we write a number in the form of a into 10 to the power of b, that is called a scientific notation. Okay, a is the number between 1 and 10. Okay, a has to be between 1 and 10. Okay, b is integer power, b has to be integer power. Power of 10 is irrelevant to the significant figures. All zeros in the base numbers are always significant. All zeros in the base number are always significant. Okay, and this number ideally should be less than 10. Okay, less than 10. Okay, in some cases we might use 11, 12, 13, 14, but 13 can be written. Suppose I write say 11 into 10 to the power of 2 can be written as 1.1 into 10 to the power of 3. This is correct way of writing significant figures. The digit should be ideally be less than 10. If it is more than 10, we have to put a decimal and transfer extra 10 into the 10 to the power value. Okay, now as you know that only these are the significant figures. So in this case also 2 significant figure, this is also 2 significant figure. So whenever we are using scientific method, okay, remember these are not significant. These 10 to the power values are not significant. Only significant thing is the number with which it is represented. So these 2, 3 are not significant. This is significant. This is significant. Okay, 11 has 2 digits. 1.1 also have 2 digits. So both are significant numbers. Okay, all zeros in the base number are always significant. Okay, so let's see one example. So here we have written a number 4.700 into 10 to the power of 2 centimeter, 4.700 into 10 to the power of 3 millimeter, 4.700 into 10 to the power of minus 3 kilometer. So the same unit, okay, same unit, we are now using scientific method, we are using scientific notation, and that is also important. When you are solving questions in future, you will always use, whenever some data will be given to you, say 10 centimeter, we will use 10 into 10 to the power of minus 2 meter. Centimeter to meter conversion is one of the most important point in scientific notation, and it will be very handy, especially when you move to second PU, when you are solving questions on electrostatics. This will save your life. Okay, so just remember that when we are using scientific notation, these all digits are significant. All the digits including zeros, everything is significant. Okay, and only this is significant. These are not significant. 10 to the power values are not significant. Only these digits are significant. Okay, if scientific notation is not used, number 1 greater than without a decimal, trailing zeros are not significant. Number with a decimal, trailing zeros are significant. The number 0 before decimal number less than 1 like 0.12050 is never significant. Okay, so these are complicated things, but scientific notation is obviously the most modern way of using significant figures. and that's why it is mostly in use as well. Now next, order of magnitude. Okay, order of magnitude is important. So when we say in a result a into 10 to the power of b, round a into 1 if a is less than 5, or to 10 if a is between 5 and 10. Okay, number. So for example, if I say what is the meaning of that? So here we have a example. Diameter of earth is 1.28 into 10 to the power of 7 meter. Here we will say order of 10 to the power 7 meter. Okay. So if I say that a number, say 7 into 10 to the power of 7. What is the order of this number? Order of this number is 10 to the power of 8. Okay, 10 to the power of 8 order. Why 10 to the power of 8? Because if you see this number, this is greater than 5. This number is greater than 5. So whenever a number is greater than 5, when you are writing the order, okay, order, okay, order will be, what you have to do, you have to take this number to be 10. 7 will become 10, and 10 means what? 10 to the power value will increase by 1. So it will be 10 to the power of 8 order. But if the number is less than 5, okay, then we will, or less than equals to 5, then we will use this to be same order as the original thing. So here 1.28 is less than 5. Okay, so we will use 10 to the power 7 order. So the diameter of earth is of the order of 10 to the power of 7 meters. So this is a approximate representation. It is not giving you exact value, but that will give you a closest 10 to the power representation. Okay, diameter of hydrogen atom. Diameter of hydrogen atom is 1.06 into 10 to the power of minus 10 meter. Order of 10 to the power of minus 10 meter. Okay, so earth is 10 to the power of 7 orders of magnitude larger than hydrogen. So when you are comparing earth and hydrogen atom, okay, then you will see that this is 10 to the power of 7 or order of 17 orders. 17 order means 10 to the power 17. So if I say that your score is second order more than some other person's score, that means you are scoring 100 times more than the other student, right? So just for your information, that this is just a academic purpose. In our colloquial term, in our use daily uses, we use this kind of term. So this is 10 to the power 7 order, 7th order. 7th order means 10 to the power 7. 10 minus 10th order means 10 to the power of minus 10 order. Okay, so quick mental sizing tool for physicists compares sizes instantly. So this is mainly used for comparing sizes, masses. Okay, so mainly for length and masses we use this tool. Okay, mental tool. It is used by head. It is not a physical tool. It's a mental tool. Okay, mental tool means that is used by the brain itself. Now another very important thing is exact number. Exact number means, suppose I say 1 dozen, 1 dozen, 2 dozen. Okay, so when you say exact number, that number has infinite precision. So 1 dozen is an infinite precise number. Okay, so multiplying, dividing factors from formula are exact. Now we are doing some so exact numbers are infinite precision. Example is 1 dozen. Okay, now multiplying and dividing factors from formula are exact. For example, if you are doing say r is equal to d by 2, okay, or s equals to 2 pi r, okay, factor 2 is exact. Okay, we can write this factor as 2, 2.0, 2.00, 2.40 as needed. Okay, so if I say 2 pi r or d by 2, so these numbers are exact numbers and they are infinitely precise. Okay, so any number which is exact, they are infinitely precise. We are not saying that radius is d by 2, it can be 2.1, it can be 2.01, it can be 2.2, no, right? It is exactly 2. Okay. Now another number is pi. Pi is 3.41452926 dot dot dot, known to be a very large number of significant figures. Take pi is equal to 3.142. For most practical cases, we take 3.14 with a limited sig figs as the specific case requires. Okay. So pi is a number, okay, having almost infinite significant figures. So there used to be a book where you can find significant figures of book, pi. Okay, the people used to remember the pi value. Okay, and there was a time when remembering pi was like a genius person. Okay, sign of a genius person. How many digits of pi you know, or how many digits of pi you remember? So if you watch, there is a movie called Life of Pi. Okay, Life of Pi. So everyone was to call him some by some other name. Okay, then he said, my name is Pi, and he wrote the entire up to 100 significant figures on the board in his school or in his institute. Okay, and then people started calling him Pi. Okay, so he changed his name from something into Pi. Okay, so anyway, so pi is a very large significant digits. Okay, there is a book, very fat book, where it number starts with 3.414 dot 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 dot. Entire book, you continue with the pages, the numbers are keep coming, keep coming, keep coming. Okay, this is an irrational number. Any irrational number has generally have a very large significant figures, right? Now let's move on with our discussion. Next part, we are going to discuss arithmetic and uncertainty. So basically arithmetic calculations and what is uncertainty in every measurement. So that we are going to discuss next. So let's see. So basically we are discussing about certain rules, how significant figures play a very important role in case of multiplication and division. Okay, so that is basically when you are multiplying two digits, when you are dividing a digit. Okay, most of the time a calculator gives you a very wrong value without taking care of the significant figure. So when you are doing calculations based on significant figure, you need to be very precise about what should be your result. Okay, now let's look into that. Final result keeps as many significant figures as the input with the least significant figure. So when you are multiplying or dividing, okay, when you are multiplying, say two digits, for example, here it is one example is shown over here, which is basically calculating the density. Okay, mass of an object is 4.237. Mass of an object is 4.237 and volume is 2.51 centimeter cube. Okay, when you are trying to find the significant figure, when you are trying to find the density, what you will get? Density equals to 4.237 divided by 2.51. Density is mass by volume. So mass by volume, and the answer will be 1.6880478087. Absurd, right? So this is 11, 12, 13, 14 decimal places, which is completely absurd. You do not need to write these many digits. So now the question is, how many digits you will write? Some of you will write 1.68. Some of you will write 1.688 because the next digit is 0. Some of you will write 1.69, like that. But remember, what is the scientific rule says. So that is very, very important. So when you are dividing or multiplying two numbers, this is applicable for division and multiplication. Multiplication and division. When two digits are getting multiplied or divided, the final result should have the least significant digit among the multipliers or dividers. Okay, so when you see here this number 1, 2, 3, 4, 4 significant figures are there. If you see this number 1, 2, 3, 3 significant figures are there. So your answer should have smallest number between 4 and 3. So between 4 and 3, who is smallest? 3 is smallest. So your answer should have only the least number of significant figure, that is 1.69. Your answer will be 1.69. I will tell you how to do that calculation as well, but your answer should be 1.69. This is absurd and we do not do calculation like this. So from now on, whenever you are doing a calculation, whenever you are doing a division, do not write any extra digits. You are not going to get any marks for that. You do not need to write the accurate value, that is not required, because in scientific calculation the significant figure is more important than writing the exact data. Clear? So that's why when we are doing the calculation, we take the least significant figure among the digits that we are using. But this is for multiplication and division. A result cannot be more accurate than the measured values based on, right? So you do not need to get the more accurate result, because the result, the data that you are inputting, your input data is 2.51. So it is correct up to 3 significant figures. So your results cannot be more accurate than more than 3 significant figures. So that is the basic logic. You do not need to find the more accurate data. There are some tendencies among some students, they used to write the exact data. Okay, you don't need to do that. From now on, you know the scientific reason. So whenever you are calculating, you can find your result up to required significant figures only. Okay. Now applying rule number 1, light year. So let's see the formula for light year. So if you see the speed of light is 3 into 10 to the power 3.00 into 10 to the power of 8 meter per second. So 3.00 means here we have 3 significant figures. So 3 significant figure is the result here. Okay. Now 1 year, when you are calculating 1 year, you will get 365.25 days. Okay. So that is another unit. Speed of light is one data, 1 year is another data. Okay. So amount of distance traveled by light in 1 year is called 1 light year. Okay. So you have to multiply C into 1 year. Okay. So when you are seeing this one, you in the scientific notation, you will get this as 3.1557 into 10 to the power of 7 seconds. Okay. 3.1557 into 10 to the power of 7 seconds. This is in 1 year. Okay. So 1 year, this has 5 significant figures. So when you are calculating the 1 light year length, that is multiplying these two, when you multiply these two, you are getting this. Okay. When you are multiplying speed of light and 1 year, you are going to get the 1 light year. So your result in 1 year, which is the smallest between this and this, smallest is 3. So your light year should only have 3 significant figures. So that's why it is written as 9.47 into 10 to the power of 15 meter. This will also have 3 significant figures. Now there may be small numerical question based on this concept, where they might ask you that this is this value, this is the other value. What will be the answer based on up to correct significant figure? So they mention it up to correct significant figure. So significant figure, for writing your answer in correct significant figures, you are entitled for marks. Okay. If you are not doing it up to correct significant figures, the teacher might deduct 1 mark if the question is mentioned up to correct significant figure, which is very important to pay attention to. Okay. So you can multiply these two and get this data, but obviously the data will be much longer, but we have to restrict ourselves only up to 3 significant figures. Okay. Now addition and subtraction is slightly different than multiplication and division. Okay. So when you are doing addition and subtraction, final result keeps as many decimal places. So for multiplication and division, decimal place is not important. Overall number of significant figure was important. It can be in the order of decimal, it can be whole number as well. That is immaterial. Total number of significant figure was important when multiplication and division. But when you are adding or subtracting, decimal points are important rather than significant figures. Okay. When you are adding, final result keeps as many decimal places as the input with the least decimal places. So in case of addition, suppose we have a number say 5.01 plus 2.1. Suppose you are adding it. What will be the answer? Most of you will write, okay, 7.11. Wrong. Wrong. Okay. If you see, the least number of decimal places is 1 here. 2.1 only 1 decimal place. Okay. 5.01 2 decimal place. Who is smallest? 1 decimal place is obviously for smallest. So your answer will be only 7.1. Okay. Even if it is say 5.09, you still will take 7.2. In that case, it will be 7.2. Okay. So what I will tell you the rules for rounding off as well. Don't worry. So you have to apply significant figure with the rule of rounding off to get the correct answer. Okay. So final result keeps as many decimal places as the input with the least decimal places. Now, in case of addition and subtraction, there can be multiple numbers. Okay. So multiplication and division generally happens between two numbers. Multiplication possible between multiple numbers as well, but division is only possible between two numbers. But addition, subtraction both can have multiple numbers, and in that case you only need to find the least decimal place, the number with least decimal places, and then you have to find your answer. For example, here you are adding 3 digits, okay, 436.32, 227.2 and 0.301 gram. Now, if you see that out of all these numbers, this one have only 1 decimal place. This one have only 1 decimal place. So your answer should not be adding them completely and getting a result. Your answer should only contain up to 1 decimal place, that is shown over here, which is 663.8 only. Okay, there was one question that came I think in KCET some years back, where you are measuring 1 kg object and you have some certain grams of gold pieces. If you add that in the object, what will be the correct weight? So remember that if you are converting any units, you have to consider the you have to take them in the same unit, then add them. Okay, when you are adding it, you always use the significant figure rule. Okay, you always use significant figure rule whenever you are adding. In case of subtraction also, 0.307 minus 0.304. Okay, so if you see that both have 3 decimal places. Okay, so you can write this as 0.003 meter, or in terms of scientific notation it will be 3 into 10 to the power of minus 3 meters. Here by mistake do not write 3.00, that is not required, because in case of subtraction you do not need the exact significant figures. Only thing that you need to take care about is the decimal places. For addition and subtraction, decimal places. For multiplication and division, least number of significant figures. For addition and subtraction, least number of decimal places. That is very, very important. That is very, very important. Okay. Now let us discuss the rounding off rules. Okay, rounding off rules. So rounding off rules means when you have added two numbers, okay, say 5.21 and say 3.257. Suppose you have added or multiplied these numbers. Okay, you add them 5 plus 3 is 8.467. Now, according to the rule of addition, the result should have only 2 decimal places, because this has 2 decimal places and this one have 3 decimal places. Okay, so between 2 and 3, 2 is lowest. So your answer should have only 2 decimal places. That means this 7 must be dropped. This 7 must be dropped. This is called the number to be dropped. Now, based on this number which is to be dropped, you need to round off your result. Okay, that is called rounding off to rounding off to correct significant figures. Okay, when you are rounding off a number, you have to first you calculate everything, like we did in the past also. So you calculate the exact value, then you have to drop one of the numbers to get the correct significant figure. Okay, so you have to drop off one number to get the correct significant figure. So there, if you are using a scientific calculator which is banned, by the way, you can get the answer based on your significant figure. You do not need to do anything. The calculator will calculate and give you the correct significant figure. But here, obviously, normal calculators do not have that function within it. They just do the exact calculation. Now, so the number that you are dropping, why you are dropping? Because after calculating you realized you have extra digits, you have to drop it because of maybe for decimal places, maybe because of the significant figures, whatever may be the reason, you are dropping the number. Okay, for example, suppose in this case, suppose we have say 25712. Suppose you are adding these two numbers. Let me explain a little bit detail so that you will be clear about it. So, so this is the digit, right? But this has 2 decimal places, this has 5 decimal places. So between 2 and 5, obviously 2 is smallest. So you have to have the second decimal place, right? And when you are getting the second decimal place, you need to remember that these two are not even considered. These two are not even considered. Only digit that you need to consider is this 7. This must be dropped. This must be dropped. This 7 must be dropped. So when you are dropping this 7, then you what you can do is, when you are dropping this 7, only this last digit, the digit which is just after the minimum requirement, that digit has to be dropped. Other digits we do not consider. Okay, maybe it is 4, 5, 7, 8, we do not consider. Maybe it is even 9, we do not consider it. We will not consider this digit at all. Only our focus should be on this digit. They are insignificant. They are completely insignificant. Only this digit is important. So there might be some cases where you will see that after doing it 4, 6, say 4, 9, 5. You do not consider this, only this digit is important. No matter how much value it is, even if it is say 9, 9 also, we will not consider it. We will only consider this value. Okay, that is that embed in your head. Some students, what they do, okay, first they think, okay, this is 9. So first let us bring it 5, and then we will drop it, and then we will bring it 7, like that. So do not do that. That is incorrect practice. You only need to consider the digit which is after the required digits. Maybe in terms of significant figure, maybe in terms of decimals. The digit that you are dropping, only that number you need to consider. Otherwise, anything after that we will not consider at all. Okay, anything after that, especially for decimal numbers, we will not consider them at all. Now, if the digit that we are dropping is greater than 5, our life is simple, very easy. If the number is being dropped is greater than 5, we raise the previous number by 1. Okay, so the example that I was giving it to you, this number 7 is greater than 5. So what we will do, we will raise the previous number or preceding number by 1. So 8.47 will be our answer. So we just increase the previous number by 1. That's it. Story over. All the money is in our pocket. Go home. Tata, bye bye. So here, if you see that this is a 6. Okay, we are dropping this 6. So we have to raise the previous number, that is 4, by 1. So our answer will be 2.75. Clear? Easy. Next, if the digits that we are dropping is less than 5, again our life is very simple. We leave the preceding digit as it is. We do not do anything. So 1.743, we are only dropping this number completely. We leave the number as it is, 1.74. We just drop the number. Just drop the number without doing anything else. Okay, so he is like extra, go away. Okay, if the number is more than 5, we add one number back. If the number is less than 5, we say go home, don't come back, tata bye bye, right? Now, if the digit is to be dropped is exactly equals to 5, then there is a condition that we need to obey. Okay, if the number that we are dropping is exactly equals to 5, then we have to consider two things, two very important things. If the previous number is an even number or it's an odd number. Okay, so if you are someone who is familiar with flow chart, let me give you a flow chart. Okay, so number to be dropped. Okay, this is the number to be dropped. Okay, it is greater than 5, greater than 5, then plus 1 to the previous number. Okay, if it is less than 5, I think this greater than and less than can cause confusion. So let me write it like this: greater than 5. Here it is less than 5. So in that case, just drop it. Okay, just drop it. It is equals to 5. The number that you are dropping is exactly equals to 5. Okay, then it comes two conditions. The previous number is odd or even. If it is odd, what we need to do? Raise by 1, same as this one. Okay, if it is even, then just drop it, just like this one. Okay, I think I should have do it like this. It should be easier to remember. Okay, so if it is even number, then you just drop it. Drop it means leave it. Okay, if it is odd number, plus 1 the previous number. Okay, add 1 to the previous number. Okay, so that's it. So if the dropped digit is 5, preceding number is even, then you just simply drop it. So 2.745 becomes 2.74. If the number that is to be dropped is exactly equals to 5, but the preceding digit is odd, then raise the preceding digit by 1. So for example, 2.735, that will become 2.74. So 2.745, 2.735, both have the same digit, 2.74. Interesting, isn't it? So if the number is odd, we make it even. If it is even, we leave it even, we do not do anything. So if you just fix your mind in that number even, previous number is even, okay, we will leave it even, we will not touch it, we will drop the 5. If it is odd, oh, you have to make it even by adding 1, and we drop the 5 later, right? So this is how we do the, so I know many of you, most of you, 99% of you will do 2.745, they will say 2.75, right? So 2.745 is not 2.75, it is 2.74 only. Okay, now let's move on with multi-step calculations. Okay, keep one extra digit. So whenever you are calculating any numerical questions, any problems, okay, you have to remember that you need to keep one extra digit at the end. So reciprocal of 9.58 rounded off to 3 significant figures. So that is the question. So when you calculate 1 by 9.58, you are going to get 0.014. Okay, now 1 by 0.014 is equal to 962, which is actually the original digits is more than 1. Okay, so what you have to do, you need to keep one extra digit, okay, and then you have to keep the significant figures. Okay, so if you are doing it, try to keep one extra digit, that gives you little bit more accuracy. Working rules in intermediate steps. So when you are doing intermediate step, if it is a final answer, this is your correct answer. If it is an intermediate step, you have to keep one digit extra while calculating. So do not try to apply the law of significant figures in the intermediate steps as well. In the intermediate steps, you have to keep one digit extra for each and every calculations. Okay. So in an intermediate step, retain one digit more than the significant digits required. That is a rule that you have to follow. Round off to proper significant figures only at the end of the calculation. So when you are calculating, suppose some problem is given, you are solving, oh, this is, in between when you are solving it, the value that you are writing, that should not have all the digits, that should not have the least number of digits, that should have one extra digit only. Suppose you are doing, say, s is equal to ut plus half 80 square, you are calculating 80 square. 8 into t comes out to be 27.057, but 28.057, you may need only two decimals. So 27.05. Instead of keeping up 27.05, you keep one digit extra, that is 27.057. The remaining digits you can ignore. So that is the process. Whenever you are solving, always keep one digit extra for the intermediate steps, and at the end you round it off. Okay, very precise constant may be rounded off for computation. For example, speed of light, it is 2.9, 2.9979258 can be rounded off to 3 into 10 to the power of 8 meter per second. Okay, exact numbers. Okay, 2 pi in t is 2 pi square root of time period is 2 pi square root of L by G, have infinite significant figures. Okay, so in some cases they have infinite significant figures, some cases they need to calculate. So let's see one problem. Each side of a cube is 7.203 meter. Find total surface area and volume to appropriate significant figures. So this is the question. So for a cube, this is the side length. Find total surface area and volume in appropriate units. Surface area is what? So for a cube, if you consider a cube, cube has 6 surfaces. 1, 2, 3, 4, 5, 6. A cube has 6 surfaces. Okay. Each surface is a square. Each of them is a square of AA. Okay. So what is the total surface area of a cube? Total surface area of a cube is 6 times area of one surface. Right. So 6 into 7.203 whole square. This is the surface area. Now if you calculate it, you will get your result 3.11.299254. Now how many significant figures are there? So if you see that this is a multiplication, okay, and you should not consider this is a exact number. So this is an infinitely significant. So even if you think that, okay, this is a digit 6, so that means only one significant figure is required, I will write 300. No. So this is an exact number 6. This has infinite significant figure. You should not consider its significant figure. You need to consider the significant figure of this number. How many significant figure? 1, 2, 3, 4. So 4 significant figures are there. Your answer should have 4 significant figures only. So that is super important to remember. Okay, your answer should have 4 significant figures only. So that means 311.3. You can ignore everything else, and after calculating it, you are getting 3.299. So you need to apply the law of rounding off. So rounding off means you are going to drop this 9. So this 9 is greater than 5. That means you have to increase the previous number by 1. Okay, that's how you will do it. Now what about volume? So volume is a cube for a cube. So here it is 7.203 whole cube. Again, the answer should have only 3 significant figures and 4 significant figures. So this will be 373.5 meter cube. So your answer should always have the minimum significant figures of the given value. So here this has 4 significant figure. This is also 4 significant figure. Your answer should also have 4 significant figure. Okay. So reasoning, measured length has 4 significant figures. The measured length has 4 significant figures. So area and volume also be rounded off to 4 significant figures. Okay. So area and volume must also have rounded to 4 significant figures. Clear? Now let's move on with next part, density with significant figure. Okay. So 5.74 gram of a substance occupies 1.2 centimeter cube. Express its density keeping significant figures in view. Just for practice, okay, mass is 5.74. How many significant figure? 1, 2, 3. So 3 significant figures in the mass. Volume is 1.2 centimeter cube, that is 1, 2. So it has only 2 significant figures. So between 3 and 2, who is smallest? Smallest is obviously 2. So your answer should have only 2 significant figures. So this will be when you are dividing 5.74 divided by 1.72, no matter whatever value you will get, your answer should have only 2 significant figure, which will turn out to be 4.8 in this particular case, and unit is compulsory. So whenever you are solving a question, any problem from any chapter, always keep in mind about the significant figure rule. Okay, that is very, very important. If you do it, you will never be wrong in your life. Now let us discuss about uncertainty. What is uncertainty? Uncertainty means when you are measuring a quantity, okay, not everything is perfectly measurable. There is a certain limit up to which your answer will be correct. Okay. So when you are measuring using a device, for example, say a device has a certain level of error. Okay. Always remember, any digits that you are measuring will always have a uncertainty. Uncertainty, theoretical calculation is not there, but practical example based calculations are there. Okay, exactly this example is given in your textbook. So here we are using one very simple example. A rectangular sheet is there. Okay, a rectangular sheet is there. Okay, it has some length, some breadth. Okay, the length is calculated to be 16.2 plus or minus 0.1 centimeter. Okay, so 16.2 is the exact value. This plus or minus 1 centimeter, 0.1 centimeter is the uncertainty. This is called uncertainty. This is uncertainty. That means this value is not predictable. It can either be 16.1 or it can be 16.3. So between 16.1 and 16.3, you are getting this result. That's why it is called uncertainty. Now uncertainty can come because of various factors. We are not going into that, but this is the uncertainty. Now how to solve a problem which involves uncertainties? So very important, because when you are the breadth also have an uncertainty of 0.1. So when you are calculating the uncertainty, whether they will be added or subtracted, because they have both plus or minus. So can you just simply add them, or can you simply subtract them and you say that okay, both of them have, this one have plus uncertainty, this one has minus uncertainty, so they will cancel each other. It is not like that. Uncertainties are always plus or minus. Okay, uncertainty can be positive, uncertainty can be negative, and always uncertainty is written not only with positive or only positive or only negative. It is always written as plus and minus. Plus and minus symbol represents uncertainty. Okay, if you are measuring a quantity, if there is a quantity is represented as plus and minus, that means it is the uncertainty term. Now how to calculate uncertainty? First you have to convert the uncertainty into percentage. So how to convert this into percentage? Obviously 0.1 was the uncertainty, the value is 16.2 into 100, this will be the percentage. Okay, and if you calculate it, it will turn out to be 0.6%. Okay, similarly, you need to convert this into percentage as well. So 0.1 by 10.1 into 100%. Okay, this will be 1%. We need to round it off as well, up to one decimal, up to one significant figure, and you will see that this is 0.6%. This is 1%. So once you have converted the uncertainty into percentages, the percentage based uncertainties can be added directly. These numbers cannot be added. Uncertainties always adds up. Uncertainties always adds up. Okay, when you have converted them into percentages. Uncertainties always adds up. Okay, percentage errors always add for a product. In not only for product, it also adds for subtraction, is also adds up for division as well. Okay, so the uncertainty when you are calculating the area, length into breadth is area 163.62 centimeter square plus or minus 1 plus 0.6, that is 1.6%. Okay, now again you need to convert it back to centimeter. Okay, centimeter square. How to do that? This is percentage. So 1.6 into 163.62 divided by 100. This is the final answer, which will come out to be 2.6 centimeter. Okay, so final answer will be, now you have to take the what was the significant figure here. Significant figure for this one was 1. Now if you take this one has significant figure of 2. How many significant figures was there? It has 3 significant figure. This also has 3 significant figure, but here your final result has 5 significant figure. So you have to change the number. How to change? First you have to drop this 6. So when you are dropping this 6, this is greater than 5. So your previous number should increase by 1. So previous number is increased by 1. Okay, and when you are dropping this 0.6, again this is greater than 5. So previous number should increase by 1. So it becomes 3. So final answer is 164 plus or minus 3. So this is very tricky, typical question asked mainly in JEE, but who knows, this is a part of the syllabus. Maybe in future you might see similar questions in KCET as well. But in JEE level exam, NEET level exam, this kind of questions are very, very common. Okay, so you convert everything into percentage, then you convert them back into the value and then take the least significant figure. Okay, match the answer's last digit to the size of the error, and writing this percentage pretends to the precision you don't have. So you should not write your answer like this. Your answer should be taken into consider about the least significant figure as well. Okay, so 3 centimeter square is the answer uncertainty in the final result. Okay, little interesting as well as little confusing as well, right? Little bit more about uncertainty rules. Combining n significant figure data. So data given to n significant figures, combined result valid only up to n significant figures. For example, so you are doing, say you are adding minus 12.9 gram minus 7.60 grams. So your answer is this is not minus, I think this is just an arrow. Okay, so your result is 5.74 gram. Okay, no, wrong. So if you see here, your digit, you are doing the subtraction. How many decimal points are there? This has only 1 decimal point. So that is why I am saying multiplication, division and addition, subtraction, they are all different rules, and it can cause confusion if you are not sure. So when you are doing it, 12.9 minus 7.06, you are going to get 5.84, but you need to drop this 4, so your answer will be 5.8 grams only. So addition, subtraction errors combine via decimal places, not via significant figures. Okay, so here also if you see that 1.02 grams plus or minus 0.01 gram, relative error is 1%. So this is called relative error. Relative error means 0.01 divided by 1.02 0.02. So take this value 0.01, divide by this value, that is 1.02, and multiply with 100 and add a percentage. This is called relative errors. Okay, relative error percentage. Okay, so absolute error, relative error can be different. Okay, if you see that same error for two different quantities. Okay, this is 1.02 gram, the error is 0.01 gram. Here it is 9.89 gram, the error is 0.01 gram. So same error for both cases, same error, but relative error here is 1%. For here it is only 0.1%. So same error can give you 10 times, 100 times absolute relative error. So relative error is important. Okay, intermediate results keep one more digit significant figure than the previous step, as I mentioned also, and relative errors are more important than absolute errors. So you should not, when you are calculating the final errors, it should not be just you cannot add the absolute errors, that will give you a wrong impression. Maybe your data have more errors than you are anticipating, right? So this is very important. When you are subtracting or multiplying, whatever you are doing, you should always add the relative errors or percentage errors. Okay, you should not consider the absolute error. This is absolute error. Absolute error means exact value, figurative value, that is called absolute error. But when you convert them into percentage, that is called percentage error or relative error. Okay. Now last part of today's session, which is dimension and dimensional analysis. Okay, even though it is mentioned 2.20 hours, 3 hours, I have supposed to give you some break in between. I am taking the class at a stretch. So if you want, you can take some pause and come back to this in a while later. But we will continue without any pause, and we will start with the 7 dimensions of the physical world. Okay, so as we say, there are 7 fundamental quantities. Okay, what are those? Mass, length, time, current. Okay, then we have temperature, luminous intensity, and amount of substances. And based on these 7, we also have to assign something which is called dimension. What is the dimension? Okay, the nature of a physical quantity is described by its dimension. The power to which base quantities are raised to represent it. So for dimensions of the base quantities are not important. But if I say that there is a quantity, there is a member which is a physical quantity which have some value, okay, and some unit. So how it is related to the base quantities? Okay, because many cases we do not use the base quantity. For example, I am giving one unit, say capacitance, which is represented by farad. Okay, how this 1 farad is related to all these quantities? So that is what is called the dimension of that quantity. Okay, different quantities have different dimensions. Basically, dimension is a way to find out how a quantity is involved with all these fundamental quantities. Okay, so this is not about unit. This is the relationship between that quantity and fundamental quantities. So for example, length's dimension is represented by third bracket L. So whenever you are talking about dimensions, dimensions are always represented using this third bracket. Okay, so after a long time you are using third bracket. Mass is represented by third bracket M, time third bracket T, current third bracket A, temperature is not represented by third bracket T, so be careful. Temperature is represented by third bracket K. Okay, luminous intensity is CD, and amount of substance is mole. Okay, so ampere, temperature, luminous intensity, and amount of substance, if you see that these 4 quantities dimension is same as their units. Okay, square bracket or third bracket is the dimensions of this quantity. So if I say a quantity, square bracket or third bracket of, right, I don't know whether you call it a third bracket or not. When I was a student, we used to call it third bracket. First bracket is this one, this is first bracket, this is second bracket, and this is third bracket. That's what we used to call it. So if I say dimension of X, we represent it using this. okay, square bracket x or third bracket x. Okay, only the nature quantity of the quantity is represented. We will see some example as well. So let's start with the example of volume. Okay, so volume, very common quantity. So volume is basically length into breadth into height. That's how we calculate volume. Now length is measured in using length, breadth is also using length, height is also a length. So when it comes to dimension, length, breadth, height, they are all same. So it will be square third bracket L, 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 L cube. So L cube is the dimension of volume. So if you see that this is independent of mass and independent on time. So mostly whenever we are talking about dimensions, we will check three quantities: mass, length and time. As we move forward, especially when you move to second PU, okay, you will see current also coming in frequently, and in for certain quantities temperature will also be there, thermodynamics etc. when we go there, but 90% of the cases it will be M, L and T. Okay, in second PU it will be M, L, T as well as A. Okay, force we have seen in our lower grades as well, father equals to ma. Okay, so it is mass into length per time square. So force is father equals to ma. Okay, F is equal to ma. So m is mass, acceleration is distance by time square. Okay, rate of change of velocity. So velocity is v by t. Velocity is s by t. Acceleration is v by t. So it will be s by t square. Okay, so when you are talking about dimension of force will be mlt to the power minus 2. This is one of the most fundamental dimension, most important dimension that you have to remember for all of your future. Okay, if you are studying anything, physics, chemistry or even engineering, this is the most fundamental dimension that you remember. If you remember this dimension, many other dimensions can be calculated from this. Obviously MLT though you already know. Apart from MLT, dimension of force is one of the most important dimension. Okay, one dimension in mass, one in length, minus 2 in time. All other base dimensions are 0. This is one of the stepping stone of all the dimensions. If you want to say father of all dimension, this is it. If you remember it, all other dimensions can be calculated, because force is a quantity which is linked with many other quantities directly, indirectly. So from there you can actually calculate dimensions of other quantities. For example, work. Okay, though when you study work, you will see that force and work are related. So if you know the relationship, you can actually find out the dimension. In other in PUC, in second PUC, you will see that force, how force is related to electric field, how force is related to other quantities, and you can find their dimensions as well, right? So that is super important, force dimension. Remember it, mlt to the power minus 2. Make it a habit, write it down on your wall that force dimension is mlt to the power minus 2. That one value you have to remember throughout your life. Magnitudes don't matter. So when you are calculating dimension, basically it is not matter how the quantity, what is the exact value of the quantity. It is only how the quantity is related with the fundamental units. Okay, initial velocity, average velocity and speed all share same dimension. Okay, it is very important. Velocity, initial velocity, average velocity, speed, dimensionally everyone is same, L to the power minus 1. So if you cut your hand, you will still bleed red. That's what some people used to say, that no matter what, we may look different, we may behave differently, but we all have same red bloods in our veins, right? So that is basically the dimensions. Dimension gives you who you are. Okay, inside you are all L to the power of minus 1, right? It can be velocity, it can be initial velocity, it can be average velocity, but in from inside everyone are same. Now dimensional formula and dimensional equation. So when you say dimensional formula, basically writing the quantity in terms of all the base dimension is this dimensional formula. So V equals m to the power 0 L cube T to the power 0 is the dimensional formula of volume. For speed, now speed and volume both are represented by V. This is capital V, this is small v. So there is a small difference between these two V's. Okay, small v speed is m to the power 0 L t to the power minus 1. Okay, force m L t to the power minus 2, and mass density m L to the power minus 3 t to the power 0. Okay, so basically when you are writing dimensional formula, even if the other quantities are not involved, you generally show it. That's it. Okay, so there are some guest appearances of m and t. So expressing or how and which base quantities represents the dimension for a physical quantity is dimensional formula, dimensional equation obtained by equating the physical quantity with its dimensional formula. That's it. Okay, not difficult. Now next part is super important, the principle of homogeneity. The principle of homogeneity. Quantities can be added or subtracted only if they have the same dimensions. Both sides of an equation must match dimensionally. So these two are super duper important point to remember. So if I want to say add 5 kg plus 5 kilometers, can we add them? It has a dimension only m. It has a dimension L. Definitely does not make any sense to add two quantities which have different dimensions. So if I say A plus B equals C, that means individually this and this, they all have same dimension. So when you are adding two quantities, they must have same dimension, no doubt about it. So dimension of A must be equals to dimensions of B. Okay, and when you are writing both on the other side of an equation, the left hand side, dimension of left hand side should be equals to dimension of the right hand side. That means this must be equals to C. Okay, so when you are writing a dimension, these two things are very important. When you are adding or subtracting two quantities, they has to be of same dimension. You cannot add two random quantities. This is not possible, right? You can add 5 kilometer and 1 centimeter. That is okay. Okay, even though the result does not change much, but you can still add them. You can convert centimeter into kilometer or kilometer into centimeter, and you can still add them because they have same dimensions. But if you want to add kilometers and kilograms, okay, or centimeters with grams, you cannot do that. Addition and subtraction wise. Okay, addition and subtraction between two separate quantities is not possible. They has to have the same dimensions. And again, when you are writing an equation, your left hand side and right hand side both should have the same dimensions as well. Now on the other hand, division is always allowed. Division, multiplication between two dimensions is always allowed. But again, if you are writing AB is equal to C, the total dimension of AB should be equals to total dimension of C. Okay, we will see one question. I think at the end of the chapter we have one KCET question which is important. We will see that. Okay, now what are the consequences of this? Velocities cannot be added to force, current cannot be subtracted from temperature, deriving a length, simplified dimension must be L. Okay, deriving a speed, both sides must have the same dimension L to the power minus 1. Unit cancel like algebraic symbol in the same way. So in case of multiplication and division, you can cancel out the units. Okay, dimensionless quantities, pure numbers and ratios of like quantities have no dimensions. Okay, angle. So angle, if I mention that angle is a supplementary unit, dimension wise it is a dimensionless quantity. Okay, dimension of angle is 0. Then why do we use? Because it is handy, it is helpful. Okay, it gives us an idea how big the angle is, but dimensionally it has 0 dimension. Okay, refractive index is another example. In other part you will see that strain is another example. If you add another example is strain, we will see that in the Mechanical properties of solid chapter, stress and strain. Strain is a dimensionless quantity. Okay. Some ratios, for example, sine, cos, log, exponential, they are also dimensionless. Okay. If I say sine theta, okay, that value has no dimension. Okay. So sine, cos, tan, they do not have any dimension. So if I say x equals to a sine theta meters. Now this meter is associated with this a, not with the sine theta. Sine theta has no dimension. Okay. This meter, if I say, you will see that in future in some cases, and in that point of time you might say, sir, you said that sine theta has no dimension, but why there is a meter written over here? Because that is associated with this constant. This can be 1 also. So if I say sine 30 meter, that means there is a 1 added or 1 multiplied with the sine theta, that has a dimension 1. Sine theta itself is dimensionless quantity. Okay, sine 30, sine 45, sine 60, they do not have any units, they do not have any dimensions. Okay, and also even if dimensionless quantity, they still might have some units. One example is supplementary unit angle. That is a dimensionless quantity, but still has units. You will find some other quantities in future as well, which have some dimensionless quantity, but still have a unit. Now let's see one important question from your PUC model paper. Consistency check kinematic equation. So we will check the consistency. Now let us drop this x naught. Okay, let's see. X equals to x naught v naught t plus half at square. This is the standard equation of motion. Generally, the x naught value is taken as 0 most cases. Okay, so this x naught do not come into the equation. So you will use s is equal to ut plus half at square. Okay, or x is equal to vt plus half at square. So this x naught value is mostly 0. X naught is your starting position, starting point. If the starting point is not 0, then there will be an x naught. Okay. Now obviously the dimension of x is what? Length. This is the distance traveled. Okay, distance traveled means length. So dimension of x is obviously L. Dimension of x is obviously L. X naught is the initial position. This is also a distance. This is also a length. So dimension of x naught is also L. Now how to first of all, how to approach this question? We have to do our left hand side dimension, and then we have to do the right hand side dimension. Now left hand side, there is only one quantity x. So dimension of x is dimension of length. Obviously distance. Now on our right hand side, we have 1, 2, 3 quantities. They are all added with the plus symbol. So we need to check dimensions of individually all of these 3 quantities. Okay, so first we will start with dimension of x naught. It is the initial position. Initial position is a position. So this is a dimension of L. What about v naught t? Now let us find the dimension of v naught t. V naught is what? V naught is speed or velocity. It is distance upon time. So distance means L, time means time, okay, into time. Okay, so just a second. So dimension of time is t, and this small t is also t. So dimension of Vt is actually also L. Okay, what about at square? Now this half is a constant, so constant do not come into picture while you are doing any dimensional analysis. So you need to calculate the dimension of at square. Okay, a is acceleration. Acceleration means what? Acceleration, if you remember, is velocity upon time. What is velocity? Velocity is distance upon time, and that divided by time. So it is s by t square. So s by t square means dimension will be s by t square, L by t square. So dimension wise, dimension of a is L by t square, and here we have t square. Okay, small t square is time, t square. So t square cancels, and you get dimension of L. So on our right hand side, what is the total dimension? L plus L plus L, right? Just erase this. So all the three quantities have the same dimension L. That means the total dimension must be L. So individually the left hand side and right hand side, they both have same dimension. That means the equation is dimensionally consistent. This is dimensionally consistent. Okay, so when you are checking any equation, always you need to check right hand side and left hand side and see if they are equal or not. If they are equal, we will say it is dimensionally consistent. If they are not, we will say they are not dimensionally consistent. Now let's see. So left hand side, we calculated the dimension for half mv square is equal to mgh. This is another equation. We will see that in our work energy chapter. Just a second. So half mv square is equal to mgh. You see the dimension on the left hand side, you see the dimension on the right hand side, both sides have the same dimension. So this is also dimensionally consistent. So there might be some other examples, you need to practice one or two. You might face one such question in your final exam. Okay. So here, so let's see, K must have a dimension of energy. Which kinetic energy formula is correct? So there are some kinetic energy formulas are given and they are asking which is possible. So here they have given some equations, say K is equal to m square v cube, K is equal to half mv square, K is equal to ma, K is equal to 3 by 16 mv square, K is equal to half mv square plus ma. Okay. So here you have to individually calculate the dimensions and see which of them have the dimension of energy, which is given by ml square t to the power minus 2. This is slightly advanced level question, but once work energy power is done, then this you should be able to answer this question. You need to find the dimension of individual quantities. So you will see this as this dimension. So only dimension wise this one and this one are matching. Okay, these two are matching with the given dimension. That means these two can be dimensionally correct. Okay, now one drawback of dimensional analysis is that dimensional analysis cannot predict the value of the constant. One drawback of dimensional method is that it cannot predict the constant, and that is one major drawback. Okay. Now let's see one more important thing, that is the derivation. One small derivation is still there. Once this derivation is done, I think this will be the almost end and we will close our discussion. Okay. Few practice questions I will give you. We are not going to solve this in today's session. Maybe in future we will solve, but today we are going to not going to solve it. So deducing relationship of simple pendulum. So simple pendulum, the time period of a simple pendulum. Okay, time period of a simple pendulum. Simple pendulum is something which, if you hang something with a string and if you release it, it oscillates. This is called simple pendulum motion. Okay. So the time period means the time required to complete one complete oscillation. Time required to complete one complete oscillation is called the time period of the simple pendulum, is dependent on two things. Time period is proportional to the length of the pendulum. It is proportional to length of the pendulum to some level. We do not know the exact how it is related, and it is also proportional to the gravitational acceleration. Again, we do not know exactly how it is related, whether it is square, whether it is cube, whether it is some other value, we do not know it. But we know that time period of pendulum depends on length and gravitational acceleration. Exactly how it depends, that we do not know, we are trying to find that out. So now, so if both of them are dependent on these two quantities, then we can write time period can be given by K L to the power A G to the power B. Here K is a dimensionless quantity. Dimensionless quantity means it has no dimension. So if you try to find its dimension, it will come out to be m to the power 0, L to the power 0, T to the power 0, same as plane angle. Okay. So if the quantity is ratio of two things or it is a constant, in some cases it can be dimensionless. It is a dimensionless quantity. Now what? This, if this is the equation we are writing, this has to be dimensionally correct. Okay, this has to be dimensionally correct. So dimension of left hand side must be equals to dimension of right hand side, right? So what is the dimension of time period? Time period means time required to complete one oscillation. So obviously it is a time, so its dimension will, obviously it will be time, so it will be t. Okay, time period t, time dimension is also t. What about L? L is the length of the wire, so this is, its dimension will be L, L to the power a. G is acceleration. What is the dimension of acceleration? I already showed you acceleration is s by t square, so that is it is L by t to the power 2. Okay, L by t square. Okay, for now we are writing it like this only. In future maybe we will change it. So this is L by t square to the power b. Okay, now let's multiply on the right hand side. Left hand side is okay. So here we get L to the power a into L to the power b by t to the power 2b, right? Or we can write this as L to the power a plus b t to the power minus 2b. Okay, L to the power a plus b into t to the power minus 2b, right? Now what? On our left hand side, what we have? We have m to the power 0, L to the power 0, t to the power 1. Okay, this is my left hand side. This is my right hand side. So obviously m is not there, m to the power 0 is also here as well. So when you are comparing these two sides, so individually all the powers of m, L and t should match. So m is not there, so m we don't need to consider. L is to the power 0. Here L is a plus b. So 0 must be a plus b. So 0 equals to a plus b or a equals to minus b. This is my equation 1. Now when you compare t, this is 1. On our left hand side we have 1 and our right hand side we have minus 2b. So minus 2b. So b is minus half. So if you go back put in equation 1, you get a equals to minus of minus half, that is half. So what is the relation? The relation that we obtain from this is time period is L to the power half, G to the power minus half. Now any quantity to the power half is square root, and if it is minus half, it is 1 by square root. Okay, so L to the power half means square root of L divided by G, and there was a constant K, so that constant K. Okay, so this is the formula for time period, and this constant K can be calculated using different method. So exactly the same method we have solved over here. Okay, even they have assumed M, which is not required in the exam. They will tell you that it is dependent on length and gravitational acceleration, how they are related. You need to do the calculation and you need to show that it is actually coming out to be K square root of L by G. Okay. Now very important point, K cannot be found using dimensions. K is a dimensionless quantity, so this value cannot be calculated using dimensional method. Actually K equals to 2 pi, giving time period equals to 2 pi root over L by G, but that is not necessary for you to show. But remember that any constants involved cannot be calculated using dimensional method. Okay, any pure number multiplying the RHS leaves the dimensions unchanged. So if it is a pure number or any constant, the dimension does not change, so your answer remains same. Okay. Powers and limits of dimensional analysis. What it can do, what is possible using dimensional method? It can check dimensional consistency, homogeneity of equations, prove an equation wrong if it fails the test, deduce relations among interdependent quantities up to 3 variables, okay, avoid committing to particular units or units conversions. Okay. So if three quantities are involved, you can calculate the intermediate relation between them. For example, I told you time period is L and T. You can have mass also involved over here. So M, L, T related anything can be calculated using dimensions. Okay. Now what it cannot do, so any unknown equations, unknown formulas, suppose you discovered a quantity, okay, I have discovered a quantity x which is dependent on mass, length and time like this. So what is the dimension of x, you can calculate, okay. So that is possible. What it cannot do, it cannot obtain dimensionless constants like k in the previous case, okay. It cannot prove an equation right. So if I say that say A equals to Vt, okay. So A equals to say no, not Vt, V equals to At, suppose I write, okay. It will not say whether this is correct or wrong. It will say this is dimensionally correct, but the correct relation also involves another quantity u plus At, okay. If u is 0, then v is equal to At, but if u is not 0, then dimensionally v is equal to At is correct. But is it a 100% correct equation? Maybe not, okay. So it will not be able to identify if any relation is 100% correct, okay. It will only be able to identify whether it is correct, wrong or right, but it will not be able to identify if the equation is perfect, okay. It only check the dimensional consistency, but it will not be able to tell you whether it is right or not, okay. Cannot give the exact relationship between quantities, okay. Cannot distinguish quantities with the same dimensions, that is work versus torque, okay. Work and torque have same dimensions, angular momentum and I think angular momentum and one more quantity have the same dimensions. It will not be able to differentiate between those quantities. It will say they are dimensionally consistent, okay. So these are something important thing that you need to remember. And another part is it will not be able to check dimensional consistency of certain equations. For example, if I say sin theta, cos theta, okay, or e to the power x, they are not, you will not be able to check whether they are correct or wrong using dimensional method, because they are dimensionless quantities, okay. Now let's look into the chapter summary. So we are almost at the end of the chapter, almost 2.5, not 2.5 or 2 hour 20 minutes, almost at the end. Physics is quantitative, 7 base quantities, each with standardized SI unit. All other units are derived. 7 base units, radian and steradian are supplementary units. And they are internationally accepted systems. Symbols are standardized: M, kg, S, A, K, mole, candela, etc. Report only significant figures, reliable digits plus first uncertain digits. So whenever you are taking a measurement, whenever you are taking doing some calculations, always report your digits in reliable digits as well as first uncertain digits. So when you are doing practicals, that is very handy for you, okay. Scientific notation removes ambiguity, okay. Division and multiplication, division, this is very important table, by the way, guys. If you really want to revise this chapter quickly, you need to save this PDF along with you. I will tell you how to download the PDF. Join our WhatsApp channel. The link of WhatsApp channel is also given in the description section. There you will be able to get this PDF, okay. Multiplication and division, least significant figures, okay. Plus and minus, least decimal places, round uncertain digits by convention, keep one extra digit mid calculation, okay. Dimensions, M, L, T, etc. describe the quantity's nature, homogeneity, checks equations, dimensional analysis can deduce relations, okay. Dimensionally consistent is not necessarily to be correct, okay, but dimensionally inconsistent is definitely incorrect. That is one thing, okay. If I say that A is equals to B, dimensionally correct, is it a physical relation? Is it correct relation? Maybe not. But if I say A is not dimensionally consistent with B, then definitely it's wrong, okay. We may not say that if A is equal to B, if this relation is correct, if they are dimensionally consistent. But if they are not dimensionally consistent, we can say they are wrong. This is not possible. Okay, so that is one very, very important part. So dimensional analysis may not say if the relationship is correct or wrong, but it will definitely say if it is wrong, then they are completely wrong. If it is not consistent, it is definitely wrong. Okay, now few try in the class question. Obviously, I am not trying it today. I am giving you entire set as a homework. Okay, you try to solve these questions as well as homework questions. Okay, and try to write the answer in the comment section below. If you have any doubts, also mention that in the comment section below. Okay, and next chapter we will be discussing motion in a straight line. Okay, if you have any questions, any discussions, don't forget to mention in the comment below, so that I can read your comments, I can understand what problems you have, if you have any doubts or not, so that I will be able to check and reply back to you. Okay, and obviously one earnest request to all of you, if you are watching for first time, don't forget to subscribe, follow us for more. I'll be back with the second chapter, motion in a straight line, very, very soon. Till then, bye.